This video is the third segment of 9.1. What are oxidizing and reducing agents? An oxidizing agent is the species that is accepting an electron, therefore being reduced. And we also will call this an oxidant. And so if you hear like, oh, I'm eating blueberries because they have antioxidants, essentially they're helping take oxidants out of your body. Anyways, and so a reducing agent is the species that supplies the electrons and therefore being oxidized, and it is our reductant. Therefore, the way to remember who's an oxidizing agent, who's a reducing agent. Identify who's being oxidized, who's being reduced, and they're the agent of the opposite, essentially. So here we have a reaction. And we go through and look at this reaction. We need to identify who's being oxidized and who's being reduced. So let's go through. So oxygen, as we know, carries a -2 oxidation state. There's 3 of them, so that's a total of a -6, right? So I'm just going to write this down here. Iron, there's 2 of them, right? And so we want to make sure we get a +6 over here to make a neutral compound. So 6 divided by 2 gives us +3. Carbon, natural state, 0. Iron, natural state, 0. Then CO, we know oxygen is -2. It's a 1-to-1 ratio, so carbon becomes +2. So iron is going from +3 to 0. Oxygen going from -2 to -2. Carbon is going from 0 to +2. So iron's becoming more negative, therefore it is being reduced. Oxygen's a spectator ion, and then carbon is going from 0 to +2. It's losing electrons, therefore it's being oxidized. So that means if iron's being reduced, that means it is the oxidizing agent. And I will shorthand it as OA. Carbon's being oxidized, which means it is the reducing agent. And I'll shorthand that as RA. So carbon is essentially the one forcing iron to be reduced. Iron is forcing carbon to be oxidized. So they are essentially the agents of the change that needs to occur, if that makes sense. Some useful oxidizing agents, just ones you're going to see very commonly, I should say. So oxidizing, remember they're oxidizing agents, so these guys are more likely to become reduced. So we have O2, ozone, acidic permanganate, so MnO4 negative, with the H plus it's acidic, acidic dichromate, F2, Cl2, concentrated HNO3, which is nitric acid, and H2O2. Useful reducing agents, so these guys are the ones that are going to become oxidized, H2, carbon, CO, SO2, and all of your reactive metals. So these are going to include your alkali metals, lithium, sodium, potassium, and your magnesium and calcium of your alkaline earth metals. So looking at classification, so we need to be able to identify who's the oxidizing agent, who's the reducing agent, because they're not always going to be, like you can't just isolate one compound as always going to be a reducing agent. Think of like in acids and bases where water was amphoteric or amphiprotic, that it has the capability of being an acid and a base. The same thing applies here because it can be an acid or a base. Water is a compound that can be a oxidizing agent and a reducing agent. So here, seeing how water is going to be an oxidizing agent. If you go through and look, so H plus, or H is going to be a +1, right? We know oxygen's -2. Oxygen, we don't really care about at this point. Sodium is a reactive metal, so it is going to be a reducing agent as listed in the previous slide. And when it reacts with sodium, H becomes its natural form, 0. So it's going from a +1 to a 0, which means it's gaining electrons, and therefore it's being reduced, making it an oxidizing agent. Then here, water, okay, we're going to look at the oxygen this time. So F2, as we saw in the previous slide, is a useful oxidizing agent, right? So it's going from neutral, and it causes oxygen to go to its natural state, which is O2, and so oxygen is going from -2 to O, so it's losing electrons, so it's being oxidized, which means it's a reducing agent. But you could have also determined that by remembering your useful oxidation and reducing agents, and then of course water is going to be the opposite. And so this is just making you aware of some compounds have the ability to be both oxidized and reduced. And because of water specifically, this is why it's a good solvent, why it makes great aqueous solutions, and why we use it essentially for everything. Is it just like with acids and bases, it has the ability to work both sides of a reaction. So more reactive metals are strong reducing agents. Because metals lose electrons, and we look at that based off the trend of ionization energy, which you can find in table 7 of your data booklet. Because they want to lose electrons, right? That means they want to be oxidized. Therefore, they make great reducing agents. How we figure this out is we will take two metals and we react them together. And if they do switch ions, looking at a precipitation reaction, so on and so forth, we can then identify who's stronger. And you're going to see this when we talk in 9.2 about voltaic cells. This creates what's called a reactivity series. So we have the capability to predict the outcome of a redox reaction between a metal and ions of another metal based off the reactivity series. So silver, if you look at this list right here, silver is the weakest reducing agent. So it's least readily becomes oxidized. It's a stable element, which is why we use silver for a lot of things. And as we move up, we move towards magnesium. So on this list, and this list is by no means comprehensive, but here magnesium is the strongest reducing agent. It is the most reactive out of this series. So it's more readily becomes oxidized because of its ability to be reactive. And so if you just need to be able to read the chart, and then we can predict, will a redox reaction occur based off placement in a reaction, and we will identify all that content later. So here, just looking at some examples. So we have zinc reacting with copper sulfate, and it's making copper with zinc sulfate. So sulfate, as we have here, that's going to be a spectator ion. So we're not going to worry about that guy. We're looking at zinc and copper and what it's doing. All right, so if I just quickly write this down as an ionic equation, because that's all I really care about. So if we have zinc is reacting with Cu2+. Copper is an ion because it's in an aqueous solution, and salts in an aqueous solution fully dissociate. That's why we don't worry about sulfate. Then we make copper and zinc ion because zinc is now in an aqueous solution, right? So if you look at this, this is called a displacement reactant, or displacement reaction, single displacement specifically. So zinc goes from 0 to +2, copper goes from +2 to 0. So we can see that the fact that zinc became an ion, it became oxidized, it was able to force copper to be reduced based on its placement in the chart. So if we look, zinc is above copper. So zinc has the capability of causing this reaction to move forward. Okay, so here we have zinc. It's already in its aqueous, so this is our ion. It's reacting with silver, who's a solid. And we want to know, will silver become the ion? And will zinc become reduced? Well, let's see where they are at on the table. Here's zinc, here's silver. Silver does not have the capability to reduce zinc because zinc is higher up on the chart. Therefore, no reaction is going to take place. Here we have iron. So iron is our ion. And we want to see if magnesium has the capability of becoming the ion, forcing the reduction of iron. So going back to our table, so we have magnesium at the top, iron below it. Magnesium, therefore, has the capability to reduce force reduction on iron because it's higher up in the reactivity series. And that's how you read that. Nonmetals follows the same concept. So the more reactive nonmetals are stronger oxidizing agents. It makes sense because nonmetals gain electrons. We want to look at the electron affinity. Who's more likely to want to gain an electron? Right? So we have the same kind of chart, and it makes sense based off placement on the periodic table. Iodine is further down the halogens than fluorine. And as we know, fluorine is the strongest agent on the periodic table. All right, so we are looking here. Does chlorine have the capability to force iodine to come out, allowing chlorine to become the ion? Okay, so we want to make sure, or we want to see that chlorine has the capability of forcing iodine to become reduced. So chlorine is higher up on the reactivity series than iodine. So that means chlorine has the ability to force oxidation of iodine so that chlorine may be reduced and become an ion. So it's the exact same thing, reading what's going on within the reaction.